Look up at the night sky, really look. Those countless pinpricks of light aren't just scattered randomly. They're part of an ancient, sprawling map, one that humanity has been trying to read for thousands of years. Think about that for a moment. Every star, every galaxy, every wisp of cosmic dust is a landmark in a story far grander than we could have ever imagined. This is the story of the mapmakers of the cosmos, how we discovered the shape of the infinite. It's a tale of curiosity, perseverance, and the sheer audacity of those who dared to ask what lies beyond. Centuries ago, our ancestors gazed at the same sky and saw patterns, constellations that told myths, guided sailors, and marked the seasons. But beneath those stories was something deeper, a longing to understand the architecture of the universe itself. Fast forward to today, and we've unlocked secrets they could only dream of. We've traced the curves of space-time, mapped the invisible threads of dark matter, and even glimpsed the echo of the Big Bang. Yet, with every discovery, the cosmos reveals new mysteries, pulling us further into its infinite embrace. So how did we get here? How did we go from drawing stick figures in the stars to unraveling the very fabric of reality? That's the journey we're about to take, one that spans ancient astronomers etching their observations into clay tablets, mathematicians bending light with equations, and modern telescopes capturing whispers from the edge of time. This isn't just a story about science, it's about the human spirit. It's about staring into the abyss and refusing to look away. By the end, you won't just see the night sky differently, you'll feel it. So let's begin. The map is waiting. The Babylonians didn't just glance at the stars, they studied them with the precision of mathematicians, carving their findings into clay tablets that would survive for millennia. Picture this: under the vast desert sky, scribes tracked Venus like clockwork, noting its position night after night. They didn't have lenses or satellites, just patience and an unshakable belief that the heavens held patterns worth decoding. Over in Egypt, priests aligned pyramids with celestial landmarks, turning tombs into eternal compasses pointing to the afterlife. These weren't just rituals, they were the first drafts of a cosmic blueprint. What's astonishing is how accurate these early maps were. The Babylonian MUL, pin tablets, for example, catalogued stars and planets with such detail that modern astronomers still reference them. They even predicted lunar eclipses by recognizing cycles hidden in the chaos, a leap of intuition that feels almost supernatural. Meanwhile, Chinese sky watchers recorded a guest star in the constellation we now call Taurus. Today, we know it as the Crab Nebula, the remnant of a supernova they witnessed in the year 1054. Their observations weren't just notes, they were time capsules, preserving moments of cosmic violence for future generations to unravel. But here's the real genius. These ancient cultures didn't just map the sky, they used it. Polynesian navigators crossed thousands of miles of open ocean by memorizing the stars, their canoes guided by constellations we still name today. The Greeks later wove these fragments into myths, but the underlying science was already there, waiting to be rediscovered. When Ptolemy penned his Almagest in the 2nd century, he stood on the shoulders of these unnamed sky watchers, compiling their scattered wisdom into the first systematic guide to the cosmos. So why does this matter now? Because every modern telescope, every space probe, every equation describing the universe's expansion traces back to those early stargazers who dared to chart the unknown. They taught us that the universe isn't just a spectacle, it's a puzzle, one we're still piecing together. Their maps were flawed, sure, but they sparked a question that drives us today. If we look closely enough, what else might the stars reveal? Claudius Ptolemy didn't just observe the night sky, he transformed it into a mathematical masterpiece. In the 2nd century, when most saw the heavens as the realm of gods, this Alexandrian scholar dared to quantify them. His Almagest wasn't merely a star catalogue, it was an intricate clockwork model of the universe, with Earth as its unmoving center. Picture celestial spheres nested like layers of an onion, each carrying planets along looping paths called epicycles. These weren't random guesses, they were calculated solutions to a puzzle that had baffled thinkers for centuries: how to explain the planet's mysterious backward motions across the sky. Ptolemy's genius lay in his numbers. By combining centuries of Babylonian observations with Greek geometry, he crafted equations that could predict a planet's position years in advance. Need to know where Mars would be on the night of your daughter's wedding? The Almagest could tell you. This precision made his Earth-centered model indispensable, even when it required bizarre contortions like equant points and off-center orbits to make the math work. So why did this flawed system dominate for 1400 years? Because accuracy often trumps truth in the short term. Sailors navigating by Ptolemy's tables reached their ports safely. Farmers planting by his calendar reaped abundant harvests. The model functioned, and that practicality bought it time until the day a Polish cleric named Copernicus peeked behind the cosmic curtain and saw the gears turning the wrong way. Yet dismissing Ptolemy as wrong misses his real legacy. He proved the universe could be mapped with numbers, setting a standard for scientific rigor that outlasted his cosmology. Those epicycles, they were the first shaky steps toward calculus. His star catalogue, it guided Galileo's telescope centuries later. Even his mistakes were fertile ground. Without geocentrism's contradictions, we might never have yearned for a better answer. The Almagest wasn't the end of cosmic mapmaking. It was the foundation stone for every discovery that followed. Nicolaus Copernicus didn't just rearrange the planets, he upended humanity's entire place in the universe. In the quiet corners of a Polish cathedral, this unassuming cleric scribbled equations that would topple Ptolemy's Earth-centered cosmos after 1400 years of dominance. His revelation was as simple as it was revolutionary. What if the Sun, not Earth, was the center? Picture the shockwaves. For generations, people had believed the heavens literally revolved around them, divine proof of their cosmic importance. Now Copernicus was saying they lived on just another spinning rock in an endless celestial dance. His masterwork, De Revolutionibus, wasn't some fiery manifesto. It was a meticulous mathematical argument, buried in dense Latin and published only as he lay dying in 1543. Why the caution? Because challenging geocentrism wasn't just academic heresy, it risked angering both church authorities and common sense. After all, no one feels Earth moving beneath their feet. Yet Copernicus had spotted flaws even Ptolemy couldn't smooth over. Those clunky epicycles, they vanished when you placed the Sun at the center. The planet's backward loops, just an illusion caused by Earth overtaking them in its orbit. Suddenly, the math became elegant, almost inevitable. But elegance alone couldn't sway tradition. For decades, even astronomers who admired Copernicus's calculations hesitated to accept HIS Chinese letter. Tycho Brahe, the era's greatest observer, proposed awkward compromise planets orbiting the Sun, which then orbited Earth, just to keep humanity somewhat special. It took Galileo's telescope spotting moons circling Jupiter, and Kepler's discovery that orbits were ellipses, not perfect circles, to cement the truth. The real triumph wasn't just accuracy. Copernicus had handed us something far more precious: cosmic humility. By dethroning Earth, he forced humanity to confront a universe that didn't revolve around us literally or metaphorically. That shift rippled far beyond astronomy, seeding the scientific revolution. If the heavens could be reimagined, what other truths might be rewritten? Centuries later, we're still answering that question every time we peer deeper into the cosmos. Copernicus didn't just give us a new map, he taught us to question the very ink it was drawn in. Tycho Brahe didn't just watch the stars, he measured them with a fanatic's precision. In the late 1500s, before telescopes even existed, this Danish nobleman turned his private island into a celestial fortress, armed with nothing but giant brass quadrants and a relentless eye for detail. Night after night, he charted the positions of planets with an accuracy unmatched for centuries, sometimes down to a single arc minute about the width of a fingernail held at arm's length. And here's the astonishing part, he did it all while believing the sun orbited Earth. Brahe's obsession wasn't just about collecting data, it was about proving that the universe could be understood through sheer, painstaking observation. His Uraniborg observatory wasn't just a workplace, it was a temple to measurement, complete with its own printing press to immortalize his findings. When a supernova blazed into view in 1572, most dismissed it as an atmospheric oddity. Not Brahe, he tracked it for 18 months, proving it lay far beyond the moon, a direct challenge to Aristotle's idea of an unchanging heavens. But his real legacy wasn't the observations themselves, it was what they made possible. Enter Johannes Kepler, Brahe's reluctant apprentice. Kepler's genius was mathematical, but his breakthroughs relied entirely on Brahe's decades of planetary records. Those scribbled notes contained tiny irregularities in Mars' orbit deviations, so slight only Brahe's instruments could have caught them. Without those clues, Kepler might never have realized planets move in ellipses, not perfect circles. So what does this mean for modern science? In an age of AI and space telescopes, Brahe's lesson is timeless. No algorithm can replace the power of meticulous, first-hand observation. The James Webb Space Telescope's stunning images, they're built on the same foundation Brahe laid, that every decimal point matters, because hidden in those details might be the next cosmic revelation. His star maps are long outdated, but his pursuit of precision still guides every scientist who dares to measure the infinite. Johannes Kepler stared at Tycho Brahe's meticulously recorded data and saw something no one else had, a hidden rhythm in the chaos. The planets weren't gliding in perfect circles as Ptolemy and even Copernicus had assumed. They moved in graceful ellipses, with the sun not at the center, but slightly off to one side like the conductor of an asymmetrical symphony. Kepler's first law shattered 2,000 years of celestial perfectionism, but he didn't stop there. His second law revealed something even more startling. Planets don't move at constant speeds. They accelerate as they near the sun, sweeping out equal areas in equal times, a delicate dance between distance and velocity. What's astonishing isn't just the discovery itself, but how Kepler got there. He didn't have calculus or supercomputers. He had quills, parchment, and brass numbers, some accurate to within 1/60th of a degree. For years, he wrestled with Mars' orbit alone, testing 70 different circular models before admitting the truth: the universe preferred ovals. His third law, published 9 years later, tied it all together mathematically. The square of a planet's orbital period equals the cube of its distance from the Sun, a universal rule linking Mercury's rapid lapse to Saturn's slow, stately procession. Kepler's genius was in seeing the forest and the trees. Where others fixated on geometry, he grasped the underlying physics, hinting at forces we'd later call gravity. His laws didn't just describe orbits, they revealed a solar system governed by mathematical harmony, where every planet moved to the same silent music. When Newton later derived his theory of gravitation, he stood on Kepler's shoulders, using those very laws as his foundation. Yet Kepler's legacy goes beyond equations. He proved that nature's truths often lurk in the deviations, the tiny mismatches between theory and observation. Those imperfections, they're where the real breakthroughs hide. From exoplanets to pulsars, modern astronomy still follows Kepler's playbook. Measure meticulously, then listen for the patterns whispering beneath the noise. Galileo Galilei didn't invent the telescope, but he turned it into a revolutionary weapon, one that shattered the universe as humanity knew it. In 1609, rumors reached him about a Dutch gadget that made distant objects appear closer. Within months, he'd refine the design, grinding lenses until his telescope magnified 20 times enough to reveal secrets hidden in plain sight. When he pointed it at Jupiter that January, he spotted 3 tiny stars near the planet, arranged in a perfect line. Night after night, he watched them dance, sometimes 4, never in the same configuration. These weren't stars, they were moons orbiting Jupiter just as our moon circled Earth. The implications were earth-shaking. If Jupiter had its own celestial entourage, then Earth wasn't the sole center of motion in the cosmos. But Galileo didn't stop there. His lens unveiled sunspots, dark blemishes on the sun's supposedly perfect surface, proving even the heavens were flawed and changing. The moon, long imagined as a smooth, ethereal sphere, became a craggy world of mountains and valleys under his gaze. Every observation chipped away at Aristotle's pristine, unchanging universe, replacing it with something far messier and far more real. The backlash was swift. Scholars refused to look through his telescope, dismissing his findings as optical illusions. How could Jupiter's moons exist if Scripture never mentioned them? Galileo's crime wasn't just challenging geocentrism. It was proving that truth could hide in the unseen, waiting for technology to reveal it. His trial and house arrest are infamous, but his real victory was irreversible. He'd given humanity a new way of knowing. Here's the deeper lesson. Galileo's telescope wasn't just a tool, it was an extension of human curiosity. Before him, astronomy relied on naked eye observations passed down from the ancients. After him, every discovery hinged on pushing vision further, whether with radio telescopes capturing whispers from black holes or Hubble photographing galaxies born in the cosmic dawn. Technology didn't just aid exploration, it redefined what exploration could be. That's why Galileo matters today more than ever. In an age where AI sifts through starlight for exoplanets and gravitational waves ripple through detectors buried underground, his legacy lives on. The universe isn't just what we see, it's what we dare to build in order to see farther. His telescope was the first bridge between human ingenuity and cosmic truth, and we've been building longer bridges ever since. Isaac Newton didn't just explain gravity, he rewrote the rules of the universe itself. In 1687, his Principia Mathematica landed like a thunderclap, revealing a cosmos bound by a single, invisible force. No longer were celestial bodies tugged by divine hands or crystalline spheres. Instead, Newton proposed something radical. Every particle of matter, from a falling apple to the distant moon, pulled every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. Suddenly, the same equation could describe a leaf drifting to the ground and Jupiter's grip on its moons. The brilliance of universal gravitation wasn't just its scope, it was its precision. Newton's laws turned Kepler's descriptive orbits into predictable, calculable paths. Take Halley's comet. When the astronomer Edmund Halley used Newton's equations to trace its past appearances, he forecast its return in 1758 with uncanny accuracy. For the first time, humanity didn't just observe the heavens, it could anticipate them. But Newton's real revolution was conceptual. By unifying Earth and sky under one physics, he erased the ancient divide between the corrupt, changeable terrestrial realm and the perfect, immutable heavens. His gravitational framework became the ultimate cosmic mapmaking tool, a set of instructions for decoding everything from ocean tides to Saturn's rings. Even the subtle wobbles in planetary orbits, later explained by Einstein's relativity, first betrayed their secrets through Newton's math, yet perhaps his most enduring gift was humility. Newton famously wrote, "If I have seen further, it is by standing on the shoulders of giants." Those giants Copernicus, Kepler, Galileo had handed him the pieces. But it was Newton who fitted them into a clockwork universe where every tick and tock followed laws we could grasp. The cosmos wasn't just knowable, it was predictable, a thought both exhilarating and unsettling. After Newton, the stars ceased to be mysteries and became milestones on a road we're still traveling today. William Herschel didn't just build telescopes, he built gateways to the stars. In the late 1700s, this German-born musician turned his backyard into an astronomical workshop, crafting mirrors so precise they could capture light from galaxies unseen by the naked eye. Night after night, he swept the heavens with his homemade reflectors, methodically counting stars in over 600 patches of sky. What he found was revolutionary. The Milky Way wasn't a hazy smear of light. It was a vast, flattened disk with our sun embedded somewhere inside it. Herschel's map, though crude by today's standards, was humanity's first real glimpse of our galactic home's architecture. His technique was deceptively simple. By assuming all stars had roughly the same brightness, he used their apparent dimness to estimate distance. The more stars he tallied in a given direction, the farther he projected the Milky Way's boundary. The result, a lens-shaped structure stretching farther than anyone had dared to imagine, with the sun perched unsettlingly close to the center. We now know his model was flawed. Interstellar dust obscured his view, and stars vary wildly in luminosity, but the core revelation held: the cosmos had structure. This discovery rippled far beyond stargazing. Herschel's work hinted at an unsettling truth: the universe might be vaster than medieval astronomers ever dreamed. When he accidentally discovered Uranus in 1781, doubling the known size of the solar system overnight, it was a preview of the cosmic-scale shockwaves to come. His sister Caroline, who logged his observations and discovered comets herself, became astronomy's first celebrated female trailblazer. Together, they proved the sky wasn't just a backdrop, it was a frontier. The 19th century's telescopes grew larger, but the real breakthrough was in understanding what light could reveal. When Joseph von Fraunhofer studied sunlight through a prism in 1814, he found dark lines slicing through the rainbow chemical fingerprints of the sun's composition. Suddenly, stars weren't just points of light, they were laboratories. Astronomers like William Huggins later trained spectroscopes on distant nebulae, splitting their glow into elemental barcodes. Some clouds were gas, but others, like the Andromeda Nebula, showed spectra-matching stars. The chilling implication: these smudges might be island universes, galaxies so far away their stars blurred together. Yet even as telescopes unveiled the universe's grandeur, they exposed our fragility. The Milky Way, once thought to encompass all creation, shrank to a single speck in a potentially infinite ocean. Herschel's star counts had opened a door, one that later astronomers like Harlow Shapley would kick wide, proving our sun wasn't central at all, but stranded in the galactic suburbs. Every leap in technology didn't just expand the map, it relocated us within it, each time further from the spotlight. The lesson of these early galactic cartographers: exploration doesn't just reveal new lands, it redefines home. Herschel's hand-polished mirrors began a quest we're still pursuing today, from radio telescopes tracing spiral arms to space probes tasting interstellar stardust. The tools have changed, but the wonder remains. If a musician with a backyard telescope could reshape humanity's place in the cosmos, what might we still uncover with the tools of tomorrow? Harlow Shapley didn't just study star clusters, he turned them into cosmic signposts, revealing a truth that would dethrone humanity yet again. In the early 1900s, astronomers still believed the Sun sat comfortably near the Milky Way center, a relic of pre-Copernican thinking. Shapley, a Missouri farm boy turned Harvard astronomer, shattered that illusion with one brilliant insight. Globular clusters, dense spheres of ancient stars orbiting the galaxy's outskirts, could serve as boundary markers. Picture these clusters as lighthouses scattered across a dark ocean. By measuring their distances, Shapley could triangulate our position within the Milky Way's vast expanse. His tool of choice was the pulsating stars known as Cepheid variables. These celestial metronomes blink at rates tied to their true brightness, allowing astronomers to calculate their distances with unprecedented accuracy. When Shapley mapped over 90 globular clusters, he found them arranged in a lopsided halo, centered not on the Sun, but on a point tens of thousands of light years away in the constellation Sagittarius. The conclusion was inescapable. We weren't the heart of the galaxy. We were off in the suburbs, orbiting a distant core like a speck of dust caught in a slow-motion whirlpool. The numbers were staggering. Shapley's work stretched the Milky Way's diameter to 300,000 light-years, 10 times larger than previous estimates. Though we now know the true size is closer to 100,000 light-years, his miscalculation didn't diminish the impact. For the second time in history, after Copernicus yanked Earth from the universe's center, humanity was demoted. The Milky Way wasn't just bigger than we'd imagined. It didn't even notice us. Yet Shapley's discovery did more than humble us. It gave us a new way to navigate the cosmos. Those globular clusters, some over 12 billion years old, became time capsules holding clues to the galaxy's violent youth. Their orbits traced the gravitational tug of dark matter long before we knew it existed. And their distribution hinted at a truth we're still unraveling. Galaxies grow by cannibalizing smaller neighbors, with clusters as the scattered bones of ancient collisions. What's poetic is how Shapley's method echoes across modern astronomy. Today, we use supernova and quasars as mile markers to map the universe's expansion. The Gaia spacecraft plots 1 billion stars in 3D, revealing the Milky Way's warped spiral arms. Each leap in mapping doesn't just expand our knowledge, it redefines our place in the story. Shapley proved we're not the center, but he also handed us the tools to find out where we truly belong. Edwin Hubble peered through the 100-inch Hooker telescope atop Mount Wilson in 1923 and saw a single star flickering in the Andromeda Nebula, a flicker that would change everything. That star, a Cepheid variable, pulsed with a rhythm that revealed its true distance, nearly 900,000 light-years away, far beyond the Milky Way's borders. In an instant, Andromeda transformed from a wispy cloud in our galaxy to an island universe of its own, a colossal spiral of stars as vast as our own. Cosmos had just grown exponentially larger, and humanity's place in it exponentially smaller. Hubble didn't stop there. As he catalogued galaxies beyond our own, he noticed something peculiar about their light. It was stretching, shifting toward the red end of the spectrum. This redshift wasn't random. The farther a galaxy was, the faster it appeared to be receding. By 1929, he'd pieced together the staggering truth. The universe wasn't static, as Einstein and others had assumed. It was expanding, carrying galaxies away from each other like raisins in rising bread dough. The implications were profound. If space was stretching now, it must have been denser in the past, a clue that pointed backward to a single, fiery origin. But Hubble's revelations went deeper than mere scale. His work forced us to confront the unnerving reality that the universe had a history, a narrative with a beginning. Those distant galaxies weren't just objects in space, they were windows into time, their light carrying echoes of epochs when the cosmos was younger, hotter, denser. The static, eternal universe of Newton and even Einstein crumbled, replaced by a dynamic, evolving cosmos with a story to tell. What Hubble gave us wasn't just new data, it was a new lens through which to see existence itself. The infinite wasn't just vast, it was alive, breathing, unfolding. And if space had a starting point, what other beginnings or endings might still lie hidden in the light of distant stars? His telescope didn't just map the heavens, it handed us the first page of a cosmic autobiography, written in starlight and redshift, waiting to be read. Hubble's discovery of the expanding universe didn't just add another chapter to astronomy, it rewrote the entire book of cosmic history. Picture a detective piecing together clues from a crime scene billions of years old. The redshift of galaxies wasn't just a measurement, it was a fingerprint, evidence that space itself was stretching, carrying galaxies apart like dots on an inflating balloon. This simple observation, now enshrined as Hubble's law, held a revolutionary implication. If the universe is growing, then rewinding the tape would collapse everything back to a single, unimaginably dense point. The Big Bang wasn't just a theory, it was the inevitable conclusion written in the light of fleeing galaxies. But the real magic lay in the details. Hubble's work gave us more than a starting gun for the cosmos, it handed us a cosmic clock. By measuring how fast galaxies were receding, astronomers could calculate backward to estimate the universe's age. Those first rough calculations suggested a mere 2 billion years younger than Earth's rocks, a paradox that humbled even Hubble. It took decades of refinements, accounting for dark energy and revised distance scales, to arrive at today's estimate, 13.8 billion years. Every adjustment wasn't just a correction, it was a reminder that the universe guards its secrets closely. Yet the most astonishing validation came from an unexpected source: static. In 1965, two radio astronomers named Penzias and Wilson stumbled upon a persistent hiss in their antenna, a whisper of microwave radiation bathing the entire cosmos. This was the afterglow of the Big Bang itself, cooled over eons to just 3 degrees above absolute zero. The cosmic microwave background wasn't just noise, it was a snapshot of the universe at 380,000 years old, its patterns encoding the seeds of all future galaxies. Hubble's fleeing galaxies had predicted it. Now, here was the smoking gun. What's breathtaking is how these pieces fit together. The redshift of starlight, the afterglow of creation, the abundance of light elements like hydrogen and helium, all converged on a single narrative. The universe began hot and dense, then expanded and cooled, condensing into galaxies, stars, and eventually us. But the story didn't end there. Hubble's law also hinted at futures we're still grappling with. Will expansion continue forever, leaving galaxies isolated in a cold, dark void? Or will gravity pull everything back in a big crunch? The answers lie in the subtle dance between dark energy and dark matter, forces we've only begun to map. Hubble's greatest gift wasn't just revealing where we came from, it was showing us that the universe has a biography. Every galaxy's flight, every photon's journey, is a sentence in a story that began in fire and may end in ice, and we're here against all odds to read it. Albert Einstein didn't just tweak Newton's laws, he rewrote the rules of gravity itself, turning the universe into a cosmic trampoline. In 1915, His theory of general relativity shattered the idea of gravity as a simple pull between objects. Instead, he proposed that massive bodies like stars and planets warp the fabric of space-time around them, creating curves that guide the motion of everything from falling apples to orbiting planets. Picture a bowling ball placed on a stretched bedsheet. The indentation it creates is like the sun bending space-time, and Earth's orbit becomes a marble rolling around the rim. But here's the mind-bending twist: this wasn't just a metaphor. Einstein's equations predicted measurable effects, like starlight curving around the sun during an eclipse, a phenomenon confirmed in 1919 that made him an overnight celebrity. What made relativity truly revolutionary was its implication for the universe's shape. If space-time could bend, then the cosmos might not be the infinite, flat expanse everyone assumed. Einstein's math hinted at something far stranger, a universe that could be finite yet have no edge, like the surface of a balloon. Just as a 2D ant crawling on that balloon would never find a boundary, our 3D universe might loop back on itself in ways we can't visualize. This wasn't mere speculation. His field equations allowed for multiple cosmic geometries: open, saddle-shaped, flat, or closed sphere-like. The fate of the universe, whether it would expand forever, collapse, or balance on a knife's edge, depended on which geometry was real. Einstein initially resisted the idea of an expanding universe, even inserting a cosmological constant into his equations to force a static solution. When Hubble's observations later proved space was stretching, Einstein called this his greatest blunder. Yet the irony is profound. That same constant now helps explain dark energy, the mysterious force accelerating the universe's expansion. His equations, it turns out, were smarter than he was. The real shock came when relativity collided with quantum mechanics. Black holes, predicted by Einstein's theory as regions where spacetime curves infinitely, became laboratories for the universe's most extreme physics. Wormholes, time dilation, and gravitational waves all emerged from his math, not as science fiction, but as observable phenomena. When LIGO detected ripples in spacetime from colliding black holes in 2015, it was a century-old prediction finally coming to life. Einstein's genius lay in seeing that the universe's blueprint wasn't written in forces or particles, but in geometry itself. The cosmos wasn't just a container for matter, it was a dynamic stage, twisting and stretching under the weight of its contents. Today, as astronomers measure the universe's curvature with billion-dollar telescopes, they're still asking the question relativity forced upon us: what shape is spacetime when no one's there to observe it? The answer might not just redefine reality, it could reveal whether we're living in a cosmic hall of mirrors or an infinite frontier with no end in sight. Arno Penzias and Robert Wilson weren't looking for the birth of the universe when they pointed their horn-shaped antenna at the sky in 1965. They were just trying to eliminate static. The persistent hiss plaguing their radio telescope wasn't coming from New York City or even Earth's atmosphere. It was everywhere, in every direction, a whisper of microwave radiation exactly 3.7 degrees above absolute zero. At first, they blamed pigeon droppings on the antenna, scrubbing it clean like frustrated janitors. But the noise remained, and its explanation would rewrite cosmic history. They'd stumbled upon the afterglow of the Big Bang itself, cooled over 13 billion years into a faint glow we now call the cosmic microwave background. This wasn't just another discovery, it was a time machine. The CMB is light from a moment 380,000 years after the universe began, when the searing plasma of the early cosmos finally cooled enough for atoms to form, releasing photons to travel freely through space. Those particles, stretched by expansion into microwaves, carry a snapshot of the universe before stars or galaxies existed. Imagine finding a fossilized raindrop from Earth's first storm. The CMB is that, but for the entire cosmos. What makes this glow revolutionary isn't just its existence, it's its pattern. When NASA COBE satellite mapped the CMB in 1992, it found tiny temperature fluctuations, variations of just 1 part in 100,000. These weren't random, they were the seeds of all cosmic structure, the gravitational footholds where matter would later clump into galaxies and superclusters. The universe's largest blueprints were encoded in whispers colder than interstellar space. Later missions like WMAP and Planck refined the picture, turning those fluctuations into a precision map of the early universe's composition. The CMB revealed that ordinary matter, the stuff of stars and planets, makes up less than 5% of the cosmos. Dark matter and dark energy, invisible and enigmatic, dominate the rest. It even hinted at the universe's geometry. The patterns matched a flat, infinite expanse, echoing Einstein's equations while deepening the mystery of what lies beyond our horizon. But the real magic lies in what the CMB doesn't show. That 380,000-year mark isn't the absolute beginning, it's the moment the universe became transparent. Before that, light was trapped in a swirling fog of ionized gas, hiding the Big Bang's first microseconds. To peer further back, scientists recreate those conditions in particle colliders, smashing atoms to mimic the universe's infancy. The CMB is the last echo of a time we can't directly see, a boundary between the knowable and the unimaginable. Pensier's and Wilson's pigeon trouble became the Rosetta Stone of cosmology, a message from the dawn of time written in thermal noise. Every time we tune a satellite dish or point a telescope skyward, we're not just observing space, we're listening to the universe's first breath, frozen in microwaves and waiting to tell us how it all began. Vera Rubin wasn't looking for dark matter when she began studying galaxy rotation in the 1970s. She was just trying to measure how stars moved. But what she found would upend our understanding of the cosmos. Armed with meticulous observations of spiral galaxies like Andromeda, Rubin charted the speeds of stars orbiting their cores, expecting them to slow down as they drifted farther from the center, just like planets in our solar system do. Instead, she found something baffling. Stars at the galaxy's edge whizzed just as fast as those near the middle. According to Newton's laws, this shouldn't happen. The visible mass of stars and gas wasn't nearly enough to hold these speeding stars in orbit. They should have flown off into the void, unless, of course, something invisible was holding them back. Rubin's discovery wasn't entirely new. Decades earlier, Fritz Zwicky had noticed similar oddities in galaxy clusters, proposing the existence of Dunkelmaterei dark matter to explain their gravitational grip. But Rubin's data was irrefutable. Galaxy after galaxy showed the same mismatch between visible mass and motion, as if each were embedded in an enormous halo of unseen material, its gravity alone keeping stars from escaping. The implications were staggering. Up to 85% of the universe's matter wasn't just hiding, it was fundamentally unlike anything we knew. It didn't emit light, absorb light, or interact with ordinary matter except through gravity. It was a cosmic ghost shaping the universe from the shadows. The hunt for dark matter's identity became one of science's greatest puzzles. Could it be exotic particles like WIMP weakly interacting massive particles left over from the Big Bang, or primordial black holes forged in the universe's first chaotic seconds? Experiments deep underground, in abandoned mines and mountain tunnels, now search for faint flashes as dark matter particles collide with ordinary atoms. Meanwhile, telescopes map the distorted light of distant galaxies, tracing the gravitational fingerprints of dark matter's hidden scaffolding. What's eerie is how much dark matter controls the cosmic dance. Without it, galaxies would never have formed in the early universe's smooth soup of matter. Its gravity acted as a seed, pulling atoms together until stars could ignite. Even now, vast filaments of dark matter stretch across the cosmos, guiding galaxies into sprawling superclusters like beads on an invisible string. Rubin's work didn't just reveal a missing ingredient, it exposed how little we truly see. The universe isn't just the glitter of stars, it's a tapestry woven with threads we can't detect. Every time we look at a galaxy, we're seeing only the spotlight on a stage built by something unseen. And that's the most humbling lesson of all. The cosmos is far stranger and far richer than the light alone can show. In 1998, two teams of astronomers made a discovery so shocking it forced us to rewrite the future of the universe. They were measuring distant supernova exploding stars so bright they can outshine entire galaxies to gauge how cosmic expansion had changed over time. Everyone expected gravity to be slowing the universe down, gradually pulling galaxies back like a ball tossed upward. Instead, the data showed the opposite. The universe wasn't just expanding, it was accelerating, as if some invisible hand had given it an extra push. The culprit, a force so baffling we still call it by a placeholder name, dark energy. This wasn't just another cosmic curiosity. Dark energy appears to make up 68% of the universe's total energy, dwarfing everything from stars to black holes to dark matter. Unlike gravity, which pulls things together, dark energy seems to stretch space itself apart, an anti-gravity effect embedded in the fabric of reality. Einstein's discarded cosmological constant, a mathematical fudge he'd called his greatest blunder, suddenly became the leading explanation. Was dark energy the vacuum energy of empty space, a relentless pressure driving galaxies apart? Or something even stranger, like a fifth fundamental force or a flaw in our understanding of gravity? The implications are staggering. If acceleration continues, the universe won't just expand, it will rip itself apart. Galaxies beyond our local group will eventually vanish over the cosmic horizon, their light stretched beyond detection. Stars will die, black holes will evaporate, and in trillions of years, the cosmos could become a cold, empty void. But here's the twist: we don't know if dark energy is constant. What if it strengthens over time, tearing atoms apart in a big rip, or weakens, allowing gravity to reclaim dominance in a catastrophic collapse? Efforts to map this mystery are already underway. Projects like the Dark Energy Survey and the upcoming Euclid telescope are creating 3D charts of millions of galaxies, tracing how their clustering and motion reveal dark energy's grip. Each new measurement tightens the noose around possible explanations, yet the enigma persists. The universe, it seems, is determined to keep its ultimate fate just out of reach. What dark energy teaches us isn't just about cosmology, it's about humility. Every time we think we've grasped the universe's rules, it reveals another layer of mystery. The cosmos isn't just expanding, it's accelerating into the unknown, daring us to keep up. And in that relentless rush, we're left with a haunting question. If 68% of reality is something we can't even define, what else might be hiding in plain sight? The Sloan Digital Sky Survey didn't just photograph galaxies, it revealed the universe's skeleton. Over 2 decades, this ambitious project scanned 1/3 of the sky, cataloging positions and distances for over 3 million galaxies. When scientists connected these dots in 3 dimensions, an astonishing pattern emerged. Galaxies weren't scattered randomly but woven into a vast cosmic web, a labyrinth of glowing filaments stretching billions of light years, separated by yawning voids so empty they could swallow 1,000 Milky Ways. This wasn't just structure, it was architecture on a scale so grand it defies earthly analogies. What's truly mesmerizing is how this web mirrors the universe's earliest whispers. The cosmic microwave background's tiny temperature fluctuations, those seeds from 380,000 years after the Big Bang evolved under gravity's relentless pull. Dark matter, invisible and mysterious, formed an invisible scaffolding first. Ordinary matter then flowed along these gravitational rivers, condensing into galaxies at the intersections like dew on a spider's web. The voids aren't accidents, they're the inverse of this process, regions where matter was siphoned away, leaving behind cosmic deserts. Modern simulations let us watch this drama unfold. Supercomputers like the Millennium Run model how dark matter's tendrils grew from nearly uniform beginnings, tracing filaments that now match the Sloan survey's maps with eerie precision. Yet puzzles remain. Why do some filaments stretch farther than predicted? Why do certain voids appear emptier than gravity alone can explain? Each anomaly hints at deeper physics, perhaps dark energies push altering the web's growth, or primordial quantum fluctuations imprinted at the universe's birth. This web isn't static. Galaxies ride the filaments like cosmic conveyor belts, drawn toward supercluster nodes where hundreds of thousands gather. Our Milky Way, for instance, is part of the Laniakea supercluster, a sprawling metropolis of galaxies flowing toward the Great Attractor, a gravitational anomaly we still don't fully understand. Meanwhile, the web keeps evolving. As dark energy accelerates expansion, distant filaments will fade from view, their light stretched beyond detection. Future civilizations might see only their local cluster, unaware of the grand design we're privileged to witness today. The lesson here is humbling. We're not just inhabitants of a galaxy, we're threads in a tapestry so vast it takes light billions of years to cross. And every new survey, from Euclid's upcoming dark energy maps to China's fast radio telescope, adds another stitch to this unfolding masterpiece. The cosmic web isn't just where we live, it's how we understand our place in a story written in gravity and shadow. The Hubble Space Telescope didn't just capture images, it shattered our cosmic perspective. Floating above Earth's distorting atmosphere since 1990, this school bus-sized observatory has turned its lens on everything from the birth of stars in the Orion Nebula to the violent deaths of supernova in galaxies millions of light-years away. But its most revolutionary gift wasn't single snapshots. It was the ability to stare for days, even weeks, at what seemed like empty patches of sky. The Hubble Deep Field images, first taken in 1995, transformed a dark speck of space no larger than a grain of sand held at arm's length into a kaleidoscope of 3,000 galaxies, each a swirling island of billions of stars. Suddenly, the universe wasn't just vast, it was crowded, teeming with more galaxies than we'd ever dared imagine. What made Hubble unique wasn't just its clarity, but its endurance. Ground telescopes battle atmospheric blur and the relentless march of daylight, but Hubble orbits beyond those limits, soaking in photons for as long as needed. When it fixed its gaze on the ultra-deep field in 2003, collecting light over 11 days, it revealed galaxies so ancient their light had traveled 13 billion years to reach us snapshots of the universe when it was a mere infant, just 400 million years old. These weren't the majestic spirals we know today, but faint, irregular blobs, the cosmic equivalent of toddler scribbles. Yet within them lay the raw material for everything that followed. The first generations of stars, the factories forging elements heavier than hydrogen and helium, the seeds of structures that would one day grow into galactic superclusters. Hubble's surprises didn't stop there. Its observations of distant supernova helped confirm the universe's accelerating expansion, proving dark energy wasn't just theoretical. It mapped the atmospheres of exoplanets, detecting water vapor and methane on worlds light years away. It even watched in real time as comet Shoemaker-Levy 9 plunged into Jupiter in 1994, a front-row seat to a cosmic collision that would have wiped out life on Earth. But perhaps Hubble's greatest legacy is how it made the infinite personal. Its iconic images, the pillars of creation, the sombrero galaxy, the butterfly nebula aren't just data points. They're works of art etching themselves into our collective imagination. They remind us that science and wonder aren't opposites but partners. Every photon Hubble captured is a message from the past, a reminder that to look up is to look back, and that the universe's story is still being written, with us as its astonished witnesses. The James Webb Space Telescope isn't just another instrument, it's a time machine with infrared eyes. Perched 1 million miles from Earth, beyond the Moon's orbit, JWST-18 gold-plated mirrors act like a colossal light bucket, gathering whispers from the universe's infancy. Unlike Hubble, which primarily sees visible light, Webb specializes in infrared wavelengths, the kind emitted by the most ancient objects in the cosmos. Why does that matter? Because as the universe expands, light from early galaxies stretches into longer, redder wavelengths like a fading echo. Hubble glimpsed galaxies back to about 400 million years after the Big Bang. JWST, it's spotting structures as early as 200 million years, a blink in cosmic time when the first stars were still flickering to life. One of JWST's first stunners was a galaxy dubbed Glass Z13, whose light traveled over 13.4 billion years to reach us. That's barely 300 million years after the Big Bang, a time theorists thought too early for such mature structures. Yet there it was, a glowing smudge defying expectations, its stars already old by cosmic standards. This single discovery sent shockwaves through astrophysics, forcing us to reconsider how quickly matter clumped together in the early universe. Were dark matter's tendrils more efficient than we thought? Did stars form under unknown conditions? Every answer JWST provides seems to birth 10 new questions. But ancient light isn't its only superpower. Webb's infrared vision cuts through cosmic dust like an X-ray, revealing stellar nurseries hidden from optical telescopes. Take the pillars of creation, Hubble's iconic portrait of towering gas columns. Webb's version isn't just a sharper image, it's a revelation. Infrared unveils hundreds of previously invisible newborn stars embedded in the pillars, their outflows sculpting the surrounding gas. These aren't just pretty pictures, they're data. By studying how stars ignite in such environments, we're decoding the recipe for planetary systems, including our own. Then there's the telescope's knack for exoplanet atmospheres. When JWST analyzed the gas giant WASP 96b, it didn't just confirm water vapor, it mapped clouds and detected haze, details once thought impossible for worlds so distant. Another study caught carbon dioxide in the skies of an exoplanet for the first time, a milestone for astrobiology. These aren't abstract discoveries, they're stepping stones toward answering whether life's ingredients exist beyond Earth. What makes JWST revolutionary isn't just its tech, it's the way it reframes our cosmic address. Every image whispers the same truth. We've been mapping the universe with a candle, and now someone's handed us a spotlight. As it peers deeper into the past and clearer into the present, one thing is certain: the maps we've relied on for decades are about to be redrawn, not at the edges, but at the very heart of what we thought we knew. Gravitational waves don't just ripple through space, they rewrite how we perceive it. When LIGO twin detectors trembled in September 2015, they weren't just picking up vibrations, they were capturing the echo of two black holes, each about 30 times the Sun's mass, spiraling into each other 1.3 billion years ago. This wasn't light or radio waves or any electromagnetic signal we'd relied on for centuries. It was space-time itself ringing like a bell, a distortion propagating at light speed that squeezed and stretched Earth by 1,000th the width of a proton. For the first time, we weren't just observers of the cosmos, we were listeners. What makes gravitational waves revolutionary isn't just their existence, it's what they reveal. Traditional astronomy is like studying a forest by flashlight, limited to what photons can show us, but black holes, by their very nature, emit no light. Neutron-star collisions, their visible fireworks are fleeting, often obscured by cosmic dust. Gravitational waves cut through all that. They carry information about events no telescope could ever see. The final milliseconds before black holes merge, the quark-gluon plasma in colliding neutron stars, even potential cracks in Einstein's relativity if the waves don't behave exactly as predicted. Already, this new sense has upended expectations. Before LIGO, most models suggested stellar mass black holes maxed out around 20 solar masses. Yet detection after detection revealed monsters upwards of 50, even 80 solar masses, remnants of stars we didn't know could exist. Then there was GW 170817, the neutron star merger that rained down gold and platinum across the cosmos while telescopes caught the glow in every wavelength from gamma rays to radio. For the first time, we witnessed the birth of heavy elements in real time, proving that your wedding ring's atoms likely began in such a cataclysm. The future of this field is even wilder. Pulsar timing arrays are hunting for low-frequency waves from supermassive black hole binaries, their signals embedded in the steady ticks of dead stars. Space-based detectors like LISA will launch in the 2030s, sensitive to mergers of million solar mass black holes from the universe's dawn. And if primordial gravitational waves, ripples from the Big Bang's first seconds, are ever detected, they could reveal quantum gravity effects at energy scales no particle collider will ever reach. This isn't just another tool in astronomy's toolbox. It's an entirely new language for decoding the cosmos. Where light shows us the universe's face, gravitational waves let us feel its heartbeat. And sometimes the most profound truths come not from what we see, but from what we feel vibrating in the dark. Exoplanets shattered our cosmic solitude in 1992 when astronomers spotted the first confirmed worlds orbiting a pulsar, a dead star that should have vaporized any nearby planets. But the real revolution came 3 years later with 51 Pegasi b, a Jupiter-sized planet, hugging its star so closely it completed an orbit in just 4 days. This wasn't just a new planet, it was a cosmic rule breaker, defying all expectations of how solar systems formed. Since then, the floodgates have opened. Over 5,000 exoplanets now populate the catalog, from super-Earths with diamond rain to rogue planets drifting untethered through interstellar space. Each discovery chips away at the old assumption that our solar system was typical, revealing instead a menagerie of worlds stranger than fiction. The Holy Grail, of course, is finding another Earth, a rocky planet nestled in the Goldilocks zone, where temperatures allow liquid water to pool on its surface. NASA Kepler telescope alone identified over 2,000 such candidates before its retirement, including Kepler 452b, a world 1,200 light-years away with a 99.7% Earth similarity index. But habitability isn't just about location. A planet's atmosphere, magnetic field, and even its star's temperament all play starring roles. Take TRAPPIST-1, a dim red dwarf with 7 Earth-sized planets, 3 of which orbit in the habitable zone. At first glance, it's a promising oasis until you factor in the star's violent flares, which might strip atmospheres like sandblasting paint off a wall. This search isn't just academic, it's existential. Every exoplanet found rewrites the Drake equation, that famous estimate of intelligent civilizations in our galaxy. With billions of potentially habitable worlds now statistically likely, the silence of the cosmos grows louder. Where is everybody? New telescopes like JWST are tackling that question by sniffing exoplanet atmospheres for biosignatures, molecules like oxygen or methane that could hint at life. In 2023, JWST detected carbon dioxide and water vapor on K218b, a Hycean world 8 times Earth's mass, but false positives lurk everywhere. Volcanic activity can mimic life's chemical fingerprints, and some planets might host exotic biochemistries we wouldn't even recognize. The hunt is also reshaping how we explore. Breakthrough Starshot aims to send gram-scale probes to Alpha Centauri at 20% light speed, while SETI radio telescopes sift the noise of the universe for engineered signals. Even if we never find life, the search forces us to confront what makes Earth unique or frighteningly ordinary. Are we a fluke, or is the universe teeming with neighbors we've yet to meet? The answer won't just fill textbooks, it'll redefine humanity's place in the story of the cosmos. The multiverse hypothesis doesn't just expand the universe, it explodes it into endless variations, each with its own laws, constants, and perhaps even versions of us. Imagine flipping through a cosmic library where every book is a self-contained reality, some with gravity so weak atoms never bond, others where time runs backward like a rewinding film. This isn't science fiction, it's a serious scientific frontier born from the math of quantum mechanics and inflationary cosmology. When Alan Guth first proposed that the early universe underwent a faster-than-light expansion, he didn't just explain why the cosmos is so uniform, he inadvertently opened the door to eternal inflation, a process that could spawn infinite bubble universes beyond our cosmic horizon. Critics argue the multiverse is untestable, more philosophy than physics, but supporters counter with subtle clues. The cosmic microwave background's so-called cold spot, a strangely barren patch of sky, could be a bruise from a collision with another universe. Or consider the fine-tuning problem. Why do fundamental constants like the strength of gravity or the mass of an electron have such precise values that allow stars, planets, and life to exist? In a multiverse, we'd simply occupy the rare bubble where the numbers lined up just right, a cosmic lottery winner oblivious to the countless failed tickets. String theory adds another layer. Its landscape of possible vacuum states suggests 10 to the power of 500 potential universes, each with different particle physics. Some might have 4 dimensions, others 11. A few could harbor life forms built from entirely unknown forces. The catch, we're forever trapped in our bubble, unable to peek beyond its edges. Yet the multiverse's real power lies in how it reframes existence. If every possible outcome unfolds somewhere, then somewhere out there, a version of you is reading these words in a universe where gravity is blue or where dinosaurs never went extinct. It's a humbling thought, not just that we're small, but that we might be one of infinite iterations, each scribbling its own unique footnote in the grand story of everything. Whether myth or reality, the multiverse forces us to confront the deepest question of all. In a cosmos without end, what does it mean to be unique? For all our celestial cartography, the universe still guards its deepest secrets like a sphinx. We've mapped billions of galaxies, traced the cosmic web's filaments, and even captured the afterglow of creation itself, yet 85% of matter remains invisible, and 70% of the universe's energy is an enigma we've barely begun to name. Dark matter's gravitational fingerprints are everywhere, from the way galaxies spin too fast to how light bends around cosmic voids. Yet its true nature eludes every detector we've buried in mountains and mines. Dark energy, that phantom force accelerating the universe's expansion, defies even Einstein's equations when we try to pin it down. These aren't just gaps in our knowledge, they're chasms, reminding us that what we've uncovered might be the mere footnotes of a grander text. Consider how recently our cosmic blind spots were revealed. Just a century ago, astronomers believed the Milky Way was the entire universe. Then Hubble proved galaxies existed beyond our own, and suddenly the known cosmos grew 100 billion times larger. Today, we face a similar pivot point. The James Webb Space Telescope's discovery of galaxies too massive, too early, challenges our models of cosmic dawn. Gravitational waves hint at black hole mergers that shouldn't exist under current physics. Even spacetime itself, the stage upon which all cosmic drama plays out, might be emergent from some deeper quantum fabric we can't yet perceive. Every answer seems to birth harder questions, like peeling an infinite onion. This isn't failure, it's the nature of exploration. The mapmakers of old knew their charts had edges marked, "Here be dragons," and our modern versions are no different. We've replaced sea monsters with singularities, but the principle holds. The boundary between known and unknown is where discovery thrives. When LIGO detected colliding black holes, or when JWST spotted distant galaxies defying expectations, these weren't endpoints, they were invitations to rewrite the rules. The real lesson lies in how we respond to these mysteries. Do we cling to comfortable theories or embrace the discomfort of not knowing? History favors the latter. Ptolemy's epicycles gave way to Kepler's ellipses. Newton's absolute space yielded to Einstein's relativity. Today's paradoxes, like why the universe's expansion rate measured nearby differs from distant observations, might be tomorrow's revolutions, clues that we're on the verge of another Copernican scale shift. So how close are we to a complete cosmic map? Perhaps that's the wrong question. The universe isn't a jigsaw puzzle waiting for its final piece. It's an endless frontier, revealing new depths with every tool we invent. Our maps will keep evolving, not because they're wrong, but because reality is richer than any single perspective can capture. The journey doesn't end when we reach the edge of knowledge. It begins anew in the uncharted territory just beyond. The next great leap in cosmic cartography isn't coming from a bigger telescope or a deeper space probe. It's unfolding in lines of code. Artificial intelligence has quietly revolutionized how we map the universe, sifting through petabytes of data with inhuman patience, spotting connections no human eye could catch. Take galaxy classification, where astronomers once painstakingly categorized spiral arms and elliptical blurs by hand. Neural networks now analyze millions of images in hours, learning to distinguish subtle variations even their creators don't fully understand. Some AI systems have discovered entirely new types of galaxies, their algorithms highlighting patterns in star distribution or dust lanes that didn't fit existing templates, cosmic outliers hidden in plain sight. What makes AI uniquely powerful is its ability to thrive in ambiguity. When the Large Synoptic Survey Telescope begins operations, it will generate 15 terabytes of data every night, more than a human could process in a lifetime. Machine learning doesn't just handle this deluge, it excels in it, teasing out faint gravitational lensing effects that betray dark matter's presence or predicting supernova eruptions days before they brighten enough for traditional detection. At Stanford, researchers trained an AI called Morpheus to analyze galaxy formations pixel by pixel, reconstructing the three-dimensional structure of cosmic webs with startling precision. Other projects use generative adversarial networks to simulate entire universes, testing how slight tweaks to dark energy's strength or the initial density of matter might alter the cosmos we see today. Perhaps most intriguing are AI's unexpected discoveries. In 2021, a machine learning algorithm scanning old radio telescope data identified strange, circular objects now called odd radio circles, massive structures a million light-years across with no clear explanation. Was it a glitch or something truly new? Even the scientists weren't sure. This is AI's real gift, not just finding needles in cosmic haystacks, but pointing out shapes in the hay we didn't know to look for. The future might see AI not just as a tool, but as a collaborator. Projects like SETI break through listen-employ machine learning to scan radio signals for signs of extraterrestrial intelligence, parsing noise for patterns too complex or subtle for human recognition. Other systems optimize telescope schedules in real time, chasing gravitational wave alerts or gamma-ray bursts before they fade. Some astronomers even speculate about autonomous space probes guided by AI, making split-second decisions about which exoplanet atmospheres to analyze or which supernova merit immediate scrutiny, a Hubble or JWST that thinks for itself. Yet for all its power, AI still reflects the biases of its training. Feed it only data from nearby galaxies, and it might miss anomalies common in the early universe. Rely too heavily on simulations, and you risk creating a cosmic echo chamber where the model only finds what it expects. The best mapmakers, human or machine, know when to question their assumptions. As we hand more of the cosmos secrets to algorithms, we're left with a humbling thought. The universe may be infinite, but our ways of seeing it are just beginning to evolve. Galaxy Zoo didn't just invite the public to look at galaxies, it turned millions of everyday people into cosmic cartographers. Launched in 2007, this groundbreaking project confronted astronomers with a problem. They had nearly 1 million galaxy images from the Sloan Digital Sky Survey, but no way to classify them all. Computers struggled to distinguish spirals from ellipticals or identify merging galaxies, tasks the human brain handles effortlessly, so they did something radical. They asked for help. Volunteers from teachers to truck drivers logged on, clicked through galaxy snapshots, and began sorting them by shape, structure, and quirks. Within months, what would have taken researchers centuries was done, revealing patterns no algorithm could have spotted. One participant, a Dutch schoolteacher named Hanny van Arkel, even discovered an entirely new celestial phenomenon, a mysterious green blob of ionized gas now called Hanny's voorwerp, Dutch for Hanny's object. This wasn't just busy work. Crowdsourcing tapped into something profound. The universe is too vast for any single group to decode alone. Projects like Zooniverse Galaxy, Zoo's parent platform, now span everything from spotting exoplanet transits to tracking penguin populations in Antarctica. When the Kepler telescope flooded scientists with light curves from 200,000 stars, it was citizen scientists who flagged the most promising dips for follow-up, leading to discoveries like Kepler 16b, a planet orbiting 2 stars straight out of Star Wars. Even Einstein at home lets volunteers donate idle computer time to analyze gravitational wave data, uncovering previously hidden neutron stars in the process. The beauty of these projects lies in their democracy. You don't need a PhD to recognize a galaxy's spiral arms or a star's flicker. Some of the most keen-eyed classifiers have been retirees, students, or even prison inmates participating through non-profit programs. This collective effort has unearthed cosmic oddities professionals might have missed, like green pea galaxies, small, intensely star-forming systems that challenge theories of galactic evolution. It's also reshaped how science gets done. When researchers at the University of Oxford needed help mapping Martian terrain for the Perseverance rover, they didn't hire more grad students. They invited the world to trace boulders and dust devils online. Beyond discoveries, citizen science fosters something deeper, ownership. Participants aren't just passive observers, they're co-authors on papers, their names etched into the scientific record alongside career astronomers. For many, it's the first time they've felt the thrill of genuine contribution, of knowing they helped add a star to the map. In an era where telescopes generate more data than any institution can process alone, the public has become an essential partner, not just in analyzing the cosmos, but in redefining who gets to call themselves an explorer. The stars have always belonged to everyone, but now, thanks to a laptop and curiosity, anyone can help write their story. And that might be the most revolutionary discovery of all. Mapping the cosmos does something strange to the human mind. It forces us to confront the limits of what we can comprehend. Every time we extend our charts further into the void, we're not just plotting stars, we're wrestling with questions that have haunted philosophers for millennia. Why does the universe exist at all? Is it finite or endless? And if it's truly infinite, what does that say about our place within it? These aren't just scientific puzzles, they're existential mirrors, reflecting back our deepest curiosities and anxieties. Consider the paradox of the cosmic horizon. Even with our most powerful telescopes, we can only see so far, about 46 billion light-years in any direction. Beyond that, the expansion of space carries galaxies away faster than their light can reach us. It's like standing in a forest where the trees at the edge vanish into fog. We know there's more out there, but it's forever hidden. This isn't a technological limitation, it's a fundamental boundary written into the fabric of reality. Yet here's the twist: the act of mapping up to that horizon changes how we see ourselves. In a universe so vast that most of it is unreachable, the very attempt to explore it becomes a kind of rebellion against insignificance. Philosophers like Karl Popper argued that science progresses by falsification, by proving what isn't true. But cosmic cartography flips that idea. When we discover a new exoplanet or trace a filament of dark matter, we're not just correcting old maps, we're expanding the territory of the possible. Each time JWST spots a galaxy older than our models predicted, or LIGO catches the ripple of a black hole collision, we're reminded that the universe operates on a logic far stranger than our textbooks. The map isn't just a record of what we know, it's a testament to how much we don't, and that's where the beauty lies. The ancient Greeks imagined the cosmos as a series of crystalline spheres, perfect and unchanging. Medieval scholars saw it as a divine hierarchy, with Earth at its base and heaven beyond the stars. Today, we know it's far wilder, a dynamic, evolving network of dark energy, quantum fluctuations, and space-time curvature. Yet every era's map, no matter how flawed, served the same purpose: to make the unknown feel just a little less terrifying. Whether etched on clay tablets or rendered in 3D simulations, our charts are less about dominion and more about connection, a way to whisper across the light years, "We see you." We're trying to understand. Perhaps that's the ultimate lesson of cosmic exploration. The answers we seek may always outpace our reach, but the act of seeking transforms us. Every time we point a telescope skyward or launch a probe into the void, we're not just collecting data, we're reaffirming a truth as old as the first campfire stories. The universe doesn't owe us clarity, but it does offer us wonder. And in that wonder, we find something unexpected. Not just the shape of the cosmos, but the shape of our own boundless curiosity. Long before telescopes or star charts, the night sky was humanity's first storybook. Ancient cultures didn't just see random dots, they traced heroes, beasts, and gods in the constellations. The Greeks envisioned Orion the hunter forever chasing the Pleiades across the heavens, while the Maya saw the dark rift in the Milky Way as a cosmic tree connecting underworld, earth, and sky. These weren't mere decorations, they were sacred maps weaving celestial patterns into the fabric of daily life, farmers planted by the rising of Sirius. Polynesian navigators recited star paths as oral atlases. Even today, when we name exoplanets after mythical figures or spacecraft after explorers, we're continuing this primordial tradition, turning the impersonal void into a landscape rich with meaning. The Renaissance transformed cosmic maps from myth into metaphor. When Copernicus displaced Earth from the universe's center, it wasn't just astronomy that shifted, it was art, philosophy, even politics. Painters like Dura depicted the new heliocentric system with almost religious awe, while John Donne lamented in poetry that the sun is lost and th Earth in this disorienting new cosmos. Centuries later, Van Gogh's Starry Night captured both the wonder and terror of an infinite universe, his swirling galaxies mirroring the turbulence of human emotion. These artistic responses reveal a profound truth. Every major leap in celestial mapping sends ripples through culture, challenging how we see ourselves. Modern science fiction shows this impact most vividly. From Star Trek's United Federation of Planets to The Expanse's asteroid belt colonies, fictional star maps reflect contemporary hopes and anxieties about exploration, colonization, and our place among the stars. Consider how differently alien worlds were portrayed before and after the Hubble Deep Field Image's early pulp fiction imagined Mars as a dying civilization, while newer stories like Arrival grapple with truly alien intelligence beyond human comprehension. The Fermi paradox, which asks why we haven't found extraterrestrial life despite the universe's vastness, has spawned entire subgenres of fiction wrestling with cosmic loneliness. Yet the deepest cultural imprint might be in how cosmic maps redefine belonging. When the Voyager probes carried golden records of Earth sounds into interstellar space, they weren't just scientific instruments, they were cosmic messages in bottles, asserting our desire to be part of a larger conversation. The overview effect, reported by astronauts, the profound shift in awareness from seeing Earth as a fragile blue marble, stems directly from our new vantage point in the cosmic map. We're no longer groundlings looking up at an alien sky. We're star-born creatures beginning to grasp our neighborhood in the galactic web. Perhaps that's the ultimate power of celestial cartography. It doesn't just show us where we are, it shapes who we imagine we could become. Whether etched on cave walls or rendered in VR, our star maps are more than navigation tools. They're mirrors reflecting humanity's endless quest to find meaning in the dark. The Vera C. Rubin Observatory perches atop Chile's Cerro Pachon like a sentinel waiting for first light, but not the kind our eyes can see. When its 8.4-meter mirror begins scanning the sky in 2025, it won't just take pictures, it will conduct the most ambitious celestial census ever attempted. Every 3 nights, its 3,000-megapixel camera will capture the entire visible southern sky, repeating the process for a decade to create a time-lapse of the cosmos in motion. We're not talking about a few thousand galaxies here. The legacy survey of space and time will track 20 billion galaxies and 17 billion stars within our own Milky Way, spotting supernova as they explode and asteroids as they tumble through our solar system. But the real treasure lies in what's invisible. The way these galaxies subtly warp and cluster will trace the hidden scaffolding of dark matter, while their accelerating expansion could reveal dark energy's grip on the universe's fate. Meanwhile, floating 1,000,000 miles from Earth at Lagrange Point 2, the Euclid telescope is already rewriting the rules of cosmic cartography. Launched in 2023, this European Space Agency mission specializes in wide-field imaging and spectroscopy across infrared wavelengths, perfect for spotting the faint distortions caused by dark matter bending light. Over 6 years, Euclid will map 1/3 of the sky, measuring the shapes and distances of over 1 billion galaxies to construct the largest 3D map of the universe ever made. What makes Euclid revolutionary isn't just scale, it's precision. By studying baryon acoustic oscillations, a frozen sound waves from the early universe imprinted in galaxy clustering, it could measure dark energy's strength with an error margin below 2%, testing whether Einstein's cosmological constant truly holds or if we need entirely new physics. These projects aren't operating in isolation. Rubin's optical depth and Euclid's infrared eyes complement each other like two detectives comparing notes. Where Rubin spots a supernova's light curve, a key tool for measuring cosmic distances, Euclid can analyze the same event's redshift to confirm its velocity. When both telescopes trace the cosmic web's filaments, their combined data will reveal whether dark matter clumps differently at various epochs, hinting at particle properties we've yet to imagine. Even their blind spots are instructive. Regions where galaxies appear sparser than expected might expose voids where dark energy's repulsive force dominates, stretching space into emptiness. The most tantalizing possibilities lie in the anomalies. If Euclid detects variations in the universe's expansion rate that defy current dark energy models, we might be staring at evidence of extra dimensions or a fifth fundamental force. Rubin's real-time sky patrol could catch a phenomenon as bizarre as a white hole, a hypothetical time-reversed black hole, or quantum fluctuations in spacetime itself. And both telescopes might finally settle the Hubble tension, the nagging discrepancy between how fast the universe is expanding locally versus measurements from the cosmic microwave background. The answer could upend our entire cosmic timeline, but beyond the hardware and algorithms, these missions share a deeper ambition. They're turning astronomy into a time machine. By stacking observations from different eras, we'll watch galaxies evolve over billions of years, tracing how dark energy's influence has changed since the universe's youth. It's like unspooling a film reel of cosmic history, except we're not just spectators. We're detectives piecing together a mystery where the clues are written in gravity, light, and the invisible threads stitching reality together. The maps we're about to make won't just fill textbooks, they might redefine what we think we know about existence itself. The universe has always whispered its secrets. Now, with Rubin's relentless gaze and Euclid's infrared vision, we're finally learning how to listen. From the Babylonians etching star patterns into clay to the James Webb Space Telescope capturing light from the universe's infancy, our cosmic cartography has always been more than mere measurement. It's been a dialogue with the infinite. Every culture that mapped the heavens did so with the tools of its time, whether naked eyes tracing constellations or algorithms decoding gravitational waves. What unites these efforts across millennia isn't just the thirst for knowledge, but the humility to recognize how much lies beyond the edges of our maps. When Ptolemy plotted epicycles or Vera Rubin charted galaxy rotations, they weren't just filling in blanks, they were redrawing humanity's place in a story too vast to comprehend. Consider how each breakthrough reshaped not just science but our sense of belonging. Copernicus didn't merely move the sun to the center, he dethroned Earth from its privileged perch, forcing us to confront our cosmic mediocrity. Hubble's discovery of expanding space didn't just add galaxies to our atlas. It revealed a universe with a beginning, a middle, and perhaps an end. Even now, as Euclid and Rubin observatories scan the skies for dark energy's fingerprints, they're challenging us to imagine futures where space itself stretches into nothingness. The maps we make are mirrors, reflecting not just where we are, but who we're becoming. Yet for all our progress, the universe remains magnificently ungraspable. Dark matter eludes detection, dark energy defies explanation, and 95% of reality's ingredients remain theoretical ghosts. This isn't failure, it's inspiration. The gaps in our knowledge are invitations, reminding us that every answer unveils new questions. When Galileo faced the Inquisition or Rubin battled skepticism about invisible matter, they proved that mapping the cosmos requires equal parts math and courage. The greatest tool in astronomy isn't a telescope, it's the audacity to keep looking when the view unsettles everything we thought we knew. What's next? Perhaps AI will spot patterns no human could, or a child gazing through a backyard telescope will notice a flicker that rewrites astrophysics. Maybe we'll finally detect life's signature in an exoplanet's atmosphere, or catch gravitational waves from the Big Bang's first seconds. Whatever comes, the journey will hinge on the same traits that guided the ancients: curiosity to question, patience to observe, and wonder to keep reaching. So here we stand on a pale blue dot suspended in a web of galaxies, holding star maps that stretch back to the dawn of civilization. They're not just charts of where we've been, they're compasses pointing to where we might go next. The universe doesn't owe us answers, but it offers endless mysteries to chase. And as long as we keep turning our faces to the sky, the greatest discovery might be this: the more we learn, the more beautifully small and impossibly significant we realize we are.